Let's start. Yeah, yesterday we stopped here for a unity feedback system given forward transfer function. I want you all to sketch the root locus, if possible using graph paper, and then we want to find K so that the system operates at a damping ratio of 0.5. Okay, we can hope you all have done it. So we should have 4 3 pole as 0, -1, -4, and then we apply the rules. So it is on to the left of odd number. So here, then we can we need to find asymptote. There should be 3 asymptote, 3 minus 0. And you need to find the real exit intercept and also the angle. Angle will be 60, 180 degrees, and 300 degrees. So it will be real exit intercept is -5/3, -2.67. Minus 1, yeah, -5/3. So is here 2.67 at 1.67, sorry. .67 is here. So 60 degrees. Normally we use ... 60 degrees, 300, and then 180 degrees. We can find breakaway point. Here, breakaway point. Finally, it is like this and like this. And this one go here. So this is the sketching that we can obtain. If you do on the graph paper, it will be clearer. So this is the one I plotted using Matlab. You can see here 3 pole, 0, -1, and -4. And we have 3 asymptote. We go here, and this is the arrow. Yeah, so normally we write K0, K0 here, K0 here. You should be able to get this. Hope you have done it. That is very, very important. So next, we want to find K. Find K. Find K for damping ratio zeta 0.5. When we need to find K, we need to do, yesterday we discussed about zeta line. Zeta line meaning this is zeta line. Angle here is cos inverse 0.5. Cos inverse 0.5 is 60 degrees. So we need to do a line here 60 degrees, zeta line. The angle is 60 degrees. If you have the graph, you can use protractor so that we have the accurate angle of 60 degrees. If you have the graph, if you have the plotting yesterday, please do it. Please plot the zeta line of 60 degrees. So that we get this point. This is the point closed loop pole give zeta 0.5. Any question on how to obtain this point? How can we obtain that point? Any question? Have you done it yesterday before the class? Anyone can help? Have you tried? Do you get any value? No response, meaning perhaps you did not do it.
Total is it 0.4 plus 0.7 J?
S equal to 0.4
0.4 plus
J
J 0.7.
0.7. Connie, you got from the graph?
Yes.
Okay, good. I want you to do because in the final exam, it will be given in a graph paper. That's why I want you to do hands-on. In the exam, you will be given root locus in a graph paper. And you will be asked to find the pole that to obtain certain specification. In this case, to obtain 0.5 damping ratio. Okay, so if you do, you get the one that what Connie obtained, 0.4 plus J 0.7 minus. So this is the point. 0.4 here, negative 0.4, J 0.7. This is the closed loop pole that gives the desired specification. Our next task is to find K. And K can be obtained by using the formula that we discussed yesterday. K is the multiplication of length of poles divided by length of zeros. So I will make a line here from this point to this. L1 to this pole L2, here L3. So you can use Pythagoras theorem to find L1, L2, L3. Or actually, if you use, if the graph is good enough, if the scale is correct, actually we can also use a ruler to get the distance. But the scale must be correct, must be similar in XY. So we normally just calculate based on the Pythagoras theorem in order to obtain L1, L2, L3. So L1 is set of 0.7 squared plus 3.6 squared. L2 is 0.7 squared plus L2 0.6 squared. L3 is 0.7 squared plus 0.4 squared. And L and K is L1, L2, L3. Divide by 1 because no 0. If we have 0, then we divide with the distance to the 0. If you calculate here, okay, please calculate what will you get? I didn't have the answer based on this point. Anyone give me the value of K?
$2.73, doctor.
2.73. You will see that from the graph, most probably all students will get slightly different answer because you read this value based on your graph, and sometimes the unit, the scale is not that big. So sometimes we have to interpret the value. That's why K, the value of K will be slightly different between each student. We will accept within a certain range. So here we get 2.73. This is the value of K that gives zeta 0.5. Okay, similarly, because the system is this system K 1 over S, S plus 1, S plus 4. The system is a third order system. We have 3 poles, 3 closed loop poles at one time. We have one here. We have one here. Actually, we have another one here. Same K, K 2.73, K here is 2.73. It will be plus 0, S equal, the closed loop pole. I will erase this. The closed loop poles will be S equal to 0.4 plus minus J 0.7. Okay. The one that we obtained at the top here is plus 0.7. And we know that all complex pole will come in pairs. We have plus, we have minus. So we also have minus here. Same K. Using K 2.73 here, we will get closed loop pole like minus 0.4 plus minus J 0.7. And please remember, because this is a third order system, we will have another pole. Where is the other pole? The other pole is given by this root locus. It's here. Remember, it starts with K0. This is another closed loop pole when K 2.73. So at one point, at 1K, there will be 3 closed loop poles. 2 is obtained by using the zeta line. The other one is obtained here. In future, in later lecture, we will be discussing on how to obtain the third pole. The third pole. It's actually obtained by using the formula K GS HS equal to 1. If we apply this formula, we add K 2.73. We know K. We add also S 0.4 plus J 0.7. We will get a formula. We get an equation, a third order equation. We will get 3 poles. If you have a calculator, you can directly calculate. If not, you can substitute this value. Then we need to find another pole. Okay, so later we will do this. We need to also find the third pole. Any question regarding this? Again, I hope you have done it. You have done the homework so that the understanding is improved. This is the one that I obtained through the Matlab. In Matlab, I can also draw zeta line. This is zeta line. This is 60 degrees. Although it looked like 45 degrees, but actually the scale is not the same in X and Y. So 60 degrees, this is the point, the closed loop pole that give zeta 0.5. You see here, so Matlab will give all the information that we need. Here, damping 0.5, almost 0.5. Difficult to get on the dot 0.5. Okay. You see here the pole mentioned minus 0.399 plus 0.696. The one that our friend is obtained just now is minus 0.4 plus J 0.7. It is close. Okay, of course, you cannot get 0.399. How can you get that value based on your graph? You will maximum get to 1 decimal place. So this is the gain. It's given here K 2.7. The one that we calculated just now is 2.73. The true value is 2.7. Of course, it is based on this pole. That's why I was saying that the value will be slightly different among all students. And it is given also overshoot 16.5, overshoot 16.5%. It is of course obtained based on zeta 0.5. We get 16.5 overshoot. Any question here? So we call this the closed loophole. S equal to minus 0.4 plus minus J 0.7. Okay, another one here. Another one here. 3 poles. But these are called dominant pole. They are dominant as compared to the third one. That's why we only consider the first two. Calculate K, we have calculated K. Calculate peak time. We want also to find peak time. And also settling time, TS, when damping ratio 0.5. This is another question which is normally asked in the exam or test. And these are important in chapter 2 in designing PID controllers. As we already have the closed loop pole, then we can of course find TS. We know that this is the one minus zeta omega n plus j omega d. Minus j omega d here. So TS, we apply the formula 4 over zeta omega n. 4 over 0.4. 10 seconds. So this system has settling time of 10 seconds. And peak time, pi over omega d, pi over 0.7. Second. 3.14 divide 0.7. Any question before we proceed? Rule number 9 that discusses the technique to calculate K is very, very important. That actually summarizes the use on how to use root locus to design a controller. This is another example. Now I want you to find K such that the closed loop system operates at 20% overshoot. 20% overshoot is obtained. Let me show. This is a graph of overshoot and damping ratio. I'm sure you have you know this. We used in the previous subject in the previous course. If we want 20% overshoot. 20% overshoot is here. 20% and is here 0.4. 1, 2, 3, 4. So 0.45 damping ratio. In the exam, you will be given the graph. Overshoot against zeta. 20% here is about 0.45 degree damping ratio. Then we have to do zeta line. This is zeta line. 0.45. I'm not sure the angle. You have to check. Theta is inverse cos 0.45. Then you need to do the angle. And then imagine, assuming that this is your graph paper, you do zeta line, you get this point. This point is given here. Minus 0.336 plus J 0.661. Now I want you to find K. In 5 minutes, please calculate the value of K. We have here a 4 pole and 1 0. Okay, now 5 minutes, calculate K. How can we get K? K is obtained by taking the length L1, L2 here, here L3, L4, L5. K is L1, L3, L4, L5 divided by L2. So all poles divide by all zeros. If you calculate, it should be around 1.71. Okay, I'm not sure. Using this pole, this value, you can use Pythagoras theorem, get the distance, and then you apply this formula. You should get about 1.71. Perhaps you get 1.7, 1.6, some 8, 6, 9, something like that. Any question? Are you okay with this? I mentioned your friend asked, will the question provide for scale? I mentioned a few times in the exam, you will be given a root locus on a graph paper. This is one example. Partial final exam. You are given, in the exam, this root locus is given. The scale is not necessarily the same. 1 cm or 2 cm, it depends. It depends on the transfer function. Because if it's large, then they have to review the scale. So you have to decide how to get the distance and how to get the angle. Okay. Sometimes the scale are the same in X and Y, sometimes different, sometimes they use 1 cm exactly, sometimes not. But you will be given the graph, you decide how to manipulate the graph. Any other question? So we have done rule number 9. We have done rule number 1 until rule number 9. By now, you should be able to sketch the root locus, and you should be able to get the information from the root locus. Basically, normally what we want is to find the closed loop poles and to find K from at that particular closed loop pole or particular point. Okay, currently, as we have software, we normally use Matlab, one of the computer-aided control system design. There are many other software that can be used. This is one of the most popular one, Matlab. So I'm here to briefly explain to you how can we use Matlab to plot and to analyze to get the data from the root locus of the root locus. Okay. So there are a few important commands that can be used in Matlab for root locus, specifically for root locus. First, this one. This is the command used to plot on Matlab. Locus, root locus. And we have to give the information in the bracket, numerator, comma, denominator, or system. System here, you have to define initially, system is numerator and denominator. This is number one, command one. Command two, if you add what we call a command here, a value here, you put in bracket RK, instead of draw the root locus, it will give you the values. R means root. R will give you root or the pole. K is the gain. So you will get a vector of R, the root, or the pole and the gain in order to plot the root locus. Another command which is important is grid, sgrid. Grid, if we use grid only, is normally for X, Y axis. Sgrid normally used for S-plane. So sgrid is normally used to, like the zeta line that I draw, I use sgrid. And we have to give the value where we want to plot the zeta line. That is number three. Number four is called rlog find, root locus find. That means if we use this command in root locus graph, we can click at any point. They will give the value of K and the closed loop poles. Okay, remember for the example that we did before, at any point there are 3 closed loop poles. So we click at any point, it will give 3 poles and the value of K. And finally, we can also click at any point on the root locus in Matlab. It will give the value. Similar to here, I click at this point. Matlab will provide us this value, all the information values. Okay, this is the zeta line that I did using Matlab. This is one example on using the command. For example, I want you to try Matlab and use this command. Okay, please try in Matlab. Okay, this is the transfer function. I give numerator equal to 1, 3. That means S plus 3. Denominator, there is many ways to define the denominators. first you can multiply together, you can open all the bracket, and then you give the values, or you can do like this. This is for s, this is s plus 2, this is for s squared, 8s plus 20. Okay, 1, 8, 20. Then you use convolution. CONV means convolution, that means you want to multiply all the poles. Okay, convolution only, there should be only 2 variables inside. So that's why I use 2 times. Convolution, denominator 1 and 2. And then I convolution also another one. Okay, so this is to define numerator and denominator. Then we use a root local numerator denominator. When we run this command, you will get this root locus. Okay, the root local show pole 0. Here are another poles. So there are 4 poles. 1, 0. The last one is grid 0.5. Is to draw the zeta line. 0.5. Okay, this is to draw zeta line 0.5. This is the command. And if you click at this point, you will get there will be a pop-up giving all these values. And this command, the second last command, giving you value of K and R, the pole and the gain. When you click at any point, let's say you click here, it will give the value. You click here, it gives the value. Okay, so this is the use of Matlab in analyzing root locus, in drawing and analyzing root locus. Hope you can try Matlab, invoke the command, run the command, and of course you can change the transfer function so that you can see how the root locus look like. And you can also use to validate your result when you calculate for the K value, or when you get the closed loop pole value, you can use Matlab to make sure that your answers are correct. Any question? We will have another class on Matlab. Oh, sorry, on root locus. We will discuss a few past year questions, past year tests, and also final exam question. If you can do earlier before class, it will be good, so that we can. So that when we discuss the answer, it will be clear. The understanding will be clearer for you if you done it before. If you read the question, if you tried before. So I would encourage you to do before class next week on the test and the final exam, past year exam examples. It is in your slide.